Hey everyone, welcome to this video. Let's do an introduction to large language models or LLMs. So, large language models or LLMs have become very popular over the past few years, and you have likely heard of or even used one, such as OpenAI's ChatGPT or Google's Gemini. As you've probably seen, LLMs are great at responding to text from humans, such as answering questions, analysis, creating content, like maybe you tell it to draft a professional email for you, etc. And large language models are large because they have a large number of weights, up to trillions of weights, and they are trained on large amounts of text, which has helped make them great at responding to text from humans. So, LLMs work by predicting the next word. They are very good at looking at previous words and then auto-completing the next words. So, for example, if I give it the text of, "Hello, my name is Kevin, how are," and I ask the LLM to predict the next word, hopefully it should say you. Or if I give it action speak and then blank, if the LLM is good, it'll predict that the next words should be louder than words. And there are two key features of LLMs that have made them great at auto-completing text. Number one is transformers, which we talked about earlier on in this course. And the next feature is training on unlabeled text. Let's talk about transformers first. A quick review of what we went over in the course. Transformers use attention, which pays more attention to important words in the text, and this makes them great at generating output where context is important. For example, I would karaoke often at the local park during my free weekends. I have gotten better at blank. Focus on the word karaoke, which I put in bold. So I have gotten better at, hopefully you predicted the word, singing. And what's cool about attention is that despite all these filler words I put in here to make karaoke be like really far away, despite all these filler words, you and attention are probably intelligent enough to ignore all these filler words and use karaoke to predict the next word of singing. And transformers also have parallelization. Attention in transformers can be trained in parallel, unlike the hidden state in a recurrent neural network. This allows the transformer to be trained much faster. So here's another example. In a RNN, if we want to calculate past hidden state 3, we have to first calculate past hidden state 1, then past hidden state 2, and then finally we can calculate past hidden state 3. That's not very efficient. Whereas with attention, we can calculate attention all in parallel or all simultaneously rather than be forced to, oh, hey, we have to first calculate the past hidden state 1, then past hidden state 2, before we can finally calculate past hidden state 3. And when it comes to training on unlabeled text, labeling text data, such as saying this text is a positive or negative review for a movie, or this text is about sports, world news, business, right? Like we categorize it. Labeling text data takes time and can be expensive. This means it was difficult to have enough text data to train a high performance model. But what if we tried something new, something else, or something new, something revolutionary? Instead of having the model train by predicting a label, have the model train by predicting the next word. There are two huge benefits to just predicting the next word. Benefit 1, you can use almost any text for training. You are not forced to only use movie reviews for training or only newspaper articles for training, right? When it came to like categorizing the categories, use them all. And the second benefit is you no longer need to label your text for training. Predicting the next word in a sequence does not require you to set labels. The next word will be the label. Another way to think of this is that any text has conveniently labeled itself for you for free. And these two huge benefits means you can train a LLM on large amounts of unlabeled text, so you are more likely to train a high performance model. So, more precisely, instead of predicting the next word, the model takes the previous tokens into account and predicts the next token rather than predict the next word, if we want to be more precise. And this is classification, so cross entropy loss is used to update the model's weights. So maybe we pass in the input text of actions speak louder than, and hopefully our model predicts that the next word or next token should be words. It goes through the model weights, or like the brain cells. It says words is the most likely next word, and the correct output is words. We calculate a cross entropy loss, use that to update the weights, and with better weights, hopefully our LLM is better at predicting the next word or next token. So behind the scenes, right, this is still what LLM does. The same diagram we've gone over again and again in this course, where we have inputs, goes to the model, the weights are used to calculate things, right? The weights are like the brain cells or the brain of the model. We get outputs, compare the outputs to the correct outputs to get a loss. That loss is like basically saying how correct or incorrect the model is. That loss is used to update the weights of the model so that the model hopefully has better weights and has better outputs or more correct outputs that lead to a lower error/loss. Now, when I first started learning about LLMs, it kind of boggled my mind. Wait a second. All this amazing stuff we see with LLMs like ChatGPT, all the amazing things it can do is just from predicting the next word or predicting the next token. That still seems like magic. How does predicting tokens or the next word give us these amazing things? Well, think of it this way. If the model is trained by predicting the next word on a large and diverse enough data, the model will not only learn about human language, but it will also learn additional knowledge about many other things as well. The additional knowledge will be contained in the model's weights, and some examples of that additional knowledge is, well, general knowledge. The name of the president during the American Civil War was, and if we have a good LLM, it'll predict that the next words or tokens is Abraham Lincoln. So somewhere in the model's weights, it knows that Abraham Lincoln was a president during the American Civil War. Or maybe we pass in text like, on Tuesdays, I like to cook pizza for lunch. Today is Wednesday, so for lunch I will not be, and then the LLM will correctly predict that I will not be cooking pizza. So by knowing how to predict tokens or next words really well, now the model has general knowledge, reasoning, and it can also do things like classification. The pizza was not worth the money or the long wait and tasted like cardboard. If someone asked me if I thought the pizza was good or bad, I will say the pizza was blank. And then the LLM will become so good at predicting next tokens or words, it will correctly predict bad right after that. So now the model is good at like analyzing sentiment or classifying things as like positive or negative, good or bad. So the first stage for training a LLM is called pre-training. For pre-training, we want both a lot of text data, diverse enough text data, and high quality text data so that the model can gain as much knowledge as possible. This text data can include articles, books, text from the internet, etc. And remember that this training text data does not need to be labeled, which saves time and money, ultimately allowing training on a lot of text data. Model weights are updated to improve next word or next token prediction, and pre-training on a lot of text data takes a lot of time and money, can be millions of dollars, so this might not be something you can just train at home on like your laptop, right? And pre-training is what uses up the most money and time when training a LLM. After pre-training, you will have a base model. The base model is now very good at next word prediction and will generate its output one word at a time. And because the base model is good at next word prediction, which, as we mentioned earlier, also means it has a lot of knowledge, like general knowledge, reasoning, classification. You can retrieve the knowledge stored in the model's weights with prompts. So maybe we'll prompt it with the text of the name of the president during the American Civil War was blank. And now we can see that the model in its weights knows that Abraham Lincoln was the president during the American Civil War. And base models are good at predicting the next word or auto-completing text, but are not as good at following instructions and answering questions. Let's see this for ourselves. Let's say we give it a prompt of role play as a lawyer explaining the Fifth Amendment to me. The ideal response, or the desired response we want from the model, is that it immediately role plays as a lawyer and explains the Fifth Amendment to me. But because the base model is only good at predicting the next word or auto-completing text, sometimes when we give it a question or an instruction, it will think it needs to auto-predict the next word to complete this as a question. So now, the base model will actually say, and how it can help me in a case. I have been charged with a crime, and I am not sure what to do. I'm experiencing a lot of fear, and your help would make a huge difference. Please explain the Fifth Amendment to me and how it can help me in this situation. Solution: certainly, I'd be happy to explain the Fifth Amendment. So do you see what's going on here? Because the base model is really good at predicting the next word, sometimes it doesn't immediately answer like an assistant. Instead, it might predict that it should, the question or instruction you give it, it predicts that it has to complete the question or complete the instruction. That is not ideal. So what's something we can do to fix this for a base model? Few-shot prompting. Learning by example is great for teaching humans. It also works for models and is called few-shot prompting when multiple examples are used. So all of this could be input text that we pass to the base model. We pass it Kevin with duplicate letters and tell it, okay, remove the duplicate letters to get Kevin back. We pass it America with duplicate letters and say, okay, you should return America back because all the duplicate letters are removed. And then we give it backpack with duplicate letters and leave this part blank. And what's awesome is that a lot of times the base model will be intelligent enough to know, okay, I should remove the duplicate letters and give backpack back. And I hope you can see where this is going. We will give it numerous examples of questions or instructions, and then where it gives will answer back, it acts like an assistant right away. Then we give it our real question or real instruction of role play as a lawyer, explain the Fifth Amendment to me, leave this part blank, and because the base model has seen these two previous examples right here, it should hopefully be intelligent enough to give us our ideal assistant response. So let's actually expand on this second example. All of this text you see in the slide will be the base model text input, where we say, oh, this is a AI assistant chat transcript. The assistant is helpful, honest, and concise. And we give the example of the assistant or the human asking a question. The assistant answers it. The human asks another question. The assistant answers it. Then we paste our real question or our real instruction here. Type in assistant and leave it blank. And hopefully, again, the base model is intelligent enough to now be a helpful assistant right away, rather than give that unideal response from earlier. So quick review. We will use large amounts of unlabeled text like articles, books, text from the internet, put it through pre-training, and we get a base model that has really good next word prediction, which leads to general knowledge, reasoning, classification, etc. It can do few-shot prompting if we want to, in some sense, trick the base model into doing what we want. But this base model is suboptimal when it comes to following instructions and answering questions. Or put more simply, it is suboptimal at being an assistant. We can somewhat fix this with few-shot prompting but it would be nice if the model could act like an assistant immediately without few-shot prompting. And that's where fine-tuning comes in. The base model has gained enough knowledge from pre-training so that it can be further fine-tuned to become an assistant. Another way to think of fine-tuning is, think of the base model as a high school graduate, where they have gained enough knowledge from kindergarten to 12th grade so that they can be further fine-tuned to become an engineer or a professor. Right? So instead of large amounts of unlabeled text, we have lots of learning with homework and tests. Instead of pre-training, we have attending school. And now we have a high school graduate that has, a lot of basic knowledge, like reading and writing, basic math, basic world history. The high school graduate has a great base, right? Base model. The high school graduate has a great base to build off of so that we can eventually turn the base model or high school graduate into an ideal assistant, which we will talk about in the next video. All right, thanks for watching. See you all in the next one.